Hey everyone, welcome back. In this episode, we are diving deep into one of the most versatile and sometimes misunderstood keywords in C++, the static keyword. If you've been programming in C++ for a while, you've likely come across static in various contexts. Inside functions, with global variables, within classes, and maybe even with class members. But what does static really mean? Why does it behave differently depending on where it's used? And how can we use it effectively? Let's break it all down step by step. In C++, static is a storage class specifier, and its meaning depends on where it's used. At its core, static changes the lifetime and visibility of variables and functions, but that definition alone doesn't help much. So let's go through the most common scenarios. Let's start with the use of static inside a function. Now, what's happening here? Normally, when you declare a local variable inside a function, it gets created every time the function is called, and it is destroyed when the function ends. But when you add the static keyword, that variable retains its value between calls. It's initialized only once, and then it lives for the entire duration of the program. So every time you call the counter function, the value of the count variable continues from where it left off. This is super useful if you need to preserve state between function calls, but you don't want to use global variables. Count is initialized only the first time, and afterwards it just increments. It's a great way to have a function level state without polluting the global namespace. Next, let's look at static when applied to global variables or functions. When you use static at global scope, it limits the visibility to the current translation unit, which usually means the current CPP file. This is known as internal linkage. Without static, a global variable or function has external linkage, meaning it can be accessed from other files using extern. So by marking something as static globally, you're basically saying this should be private to this file. This is particularly helpful in large projects to prevent name clashes and enforce encapsulation across multiple translation units. For example, if you had two CPP files that both define a function called helper and you forgot to mark them as static, you'd get a linker error. But if both are marked as static, they are invisible to each other, and you avoid the problem entirely. Now let's move on to one of the more common use cases: static within a class. In this case, count is a static member variable. What does that mean? Well, unlike regular member variables which belong to each instance of the class, a static member belongs to the class itself. That means all instances of the class share this single variable. So if you create 5 myClass objects, they don't each get their own count. They all reference the same one. To actually define that variable, you also need to initialize it outside the class, like this. It's a common pattern used for tackling object counts, limiting instantiations, or sharing common data across instances. It also works with static member functions. Here, the add function can be called without creating an object of mathutils. Why? Because it doesn't operate on instance-specific data. You just call this. Remember, static member functions cannot access non-static member variables or functions, because there is no this pointer. They operate independently of any object. Since structs in C++ are just like classes with public visibility by default, you can also use static members inside structs the same way you would use in a class. This works great for creating constants or configuration values that are shared across your program. With C++11 and beyond, you will often see this. What does this do? It declares a static member that is also a compile time constant. It can be used in array sizes, template parameters, and other compile time contexts. Because it's const_expr, you don't even need to define it outside the class unless you take its address. It's a neat and modern way to manage constants in classes. Let's take a step back and summarize the two primary roles that static plays. First, it controls lifetime. For local variables inside functions, static changes the lifetime from temporary to permanent. Second, it controls linkage. For global variables and functions, static limits their visibility to the current file, enforcing encapsulation and avoiding linkage conflicts. And in classes, it simply means the member is tied to the class, rather than an individual instance. Let's also touch on a few common mistakes. forgetting to define a static member outside the class, or trying to use the keyword this inside the static member function. Overusing static local variables where globals would be clearer, and assuming that static means private. It doesn't. Use access modifiers for that. Here are some best practices. Use static for file local helper functions. Use static member variables for shared counters or configuration values. Prefer static constants per over macros for compile time constants. Always keep in mind the lifetime implications, especially with local statics in multi-threaded environments. The static keyword is simple on the surface, but it's surprisingly powerful. It lets you manage lifetime, scope, and class behavior in precise and elegant ways. Whether you're building small utilities or large-scale applications, using static properly can help you write safer, cleaner, and more maintainable code. If you're ever unsure what static is doing in a certain context, just ask yourself two things. Is this affecting visibility across files? Or is this affecting the lifetime of the variable? That usually clears things up. Thanks so much for watching. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one.